I might as well. I'll go ahead and start recording now. But basically, yeah, I mean, you guys are responsible for knowing all those different methods. And I think of this in a lot of ways, you know, like the first time you learn anything, right? You know, you learn some baby steps, and then as you get comfortable, you start building into the other methods. And what you learn is sometimes mesh is useful, sometimes nodal is useful, sometimes the other methodologies where I just simplify the circuit's more useful, okay? And, you know, in general, especially, you know, when I'm thinking about an exam under a timed situation, if I have mesh or nodal, you know, in this case, if I'm trying to find the short circuit current, I get into situations where I've got basically 3 meshes, and that means I got 3 simultaneous equations to solve for, right? Which on an exam, sitting there with a calculator, you probably would not like to get that kind of thing on an exam, right? And so some of that is for that reason as well. So trying to get 3 equations, 3 unknowns is not fun. Even though it may be what you're comfortable with, it's not fun. So anyway, all that to say, you should know how to do the other methods. And if you get comfortable with those other methods, then they can potentially get quicker. All right, so just as an example here, so if I look at this guy right here, so what component of the short circuit current is caused by the 24-volt source, okay? So I told you a couple of things, right? So assume the short circuit current would flow from terminal A to terminal B. So that effectively means, you know, as I drew it here, that the I short circuit would be here. You know, it sort of assumes that I drew a short right there, okay? All right, so when I go down to this circuit, now notice a couple of things that I did here, and you'll notice me, I'm gonna talk about this more today, I tend to do everything more or less symbolically. All right, and for me, that's because I can look at the symbols a lot more easily than I can look at the numbers. And what I mean by that is when you're looking at the fact that the R5 in parallel with R2 is some number, that number doesn't mean as much to me as the fact that I know R2 is in parallel with R5. All right, so it's all, and especially if I use a tool like Matlab, as we'll see, we get more and more comfortable looking at the symbolic stuff. All right. So I wanted to show this. So you guys see what I did here, right? So what did I say? I basically said I wanted to find this current right here, all right? So ISC24. So what I did was I said, well, if I put a short circuit there, there's going to be essentially the circuit simplifying like that. So let me stop. Any questions about how I simplified that circuit? That should be straightforward. All right. So the next step basically is, all right, well, I have R5 and R2 in parallel with each other, right? So the way I look at this is I say, well, I've got a circuit here that has a combination of R1 in series with this parallel combination in series with R4 and R3. And I say that that current, I call it I1, is this guy right here, okay? And so if I then want to find what this current ISC24 is, right, without me, once I know this current I1, what is the step? What's the process that I would need to find this current once I know this current? Who knows? Anybody?
Simplify the circuits. The R2 and R5 is parallel.
Yeah, they're in parallel. So how can I use that fact? So how can I use the value for I1 and the fact that R2 and R5 are in parallel?
Current divider.
It's a current divider. Okay, it's a current divider. So the current I1 is dividing between those 2 branches. Now there's a formula for that. All right, but the way that I look at that simply is if I say, all right, they're in parallel with each other, they got the same voltage across them, right? If I know the current I1, then I can say the voltage across those guys is simply I1 times R2 in parallel with R5. All right, anybody disagree with that? R5. All right, then if I want to figure out what ISC24 is, I know the voltage across that resistor. So I say ISC24 is simply that voltage, I1 times R2 in parallel with R5, all over R2, like that. Now, again, there's a formula that would exist for that, right? That would be, maybe a little bit simpler, but for me, that sort of captures everything, right? In fact, oftentimes I like this kind of answering better, because when you guys, start writing stuff down, if you take the wrong approach, it can be really hard to figure out where your numbers went wrong. But I can easily see where your physics went wrong when I look at this approach. All right. Any questions about that? You guys are quiet.
I think everybody's probably comparing and contrasting with their test.
Yeah, and the chat's just literally a chat. Okay, so
Wait, why is R4 plus R3?
He's graffiti.
Oh, wait.
sorry, what was that question? Something about R4?
Yeah, why are those in series, not parallel? Is it just because don't
Why
you
is-
add the?
Well, so look at it. So basically, the way I look at this, I go back to my source. My source is sitting here. Okay, from the perspective of that source, a current's going to leave the source, right? It's going to leave here, going to go through R1, and then it's going to split between R5 and R2, and then it's going to recombine, and the same current that's in R4 and R3 is going to be in R1.
So R1, 3, and 4 are all in series then,
Yeah, and why are they in series?
because the same current.
They share the same current.
Share the same current. Now, the other thing that shares the same current is the parallel combination of R2 and R5.
So so since we took the current source out, those R4 and R3 came in series, or were they always in series?
No, that's a good point. Because the current source is out, right? If the current source was there, then R4 and R3 would not be in series.
Okay, well.
Right? Because they definitely would not have the same current going through them, right? There's a KCL that's happening at that node.
Right.
But in that case, if the 2 amp source was there, R3 and R1 would be in series.
If R3 and R1 are always in series, no matter what I do to the circuit, right? Because they are literally seeing the same current. So the thing to ask yourself is, people tend to want to just look at the picture, right? And say, well, that's in series, that's in parallel. Don't just look at the picture and say, well, they share nodes or whatever. What you want to do is you want to ask yourself is the same current flowing in those same sources or in those same devices? So R1 and R3 are always going to have the same current flowing through them, no matter what. Okay.
So what was the numerical solution for this step?
I don't know. I didn't calculate. I sent it to the TAs to do it. So I didn't. So that's why I didn't post these up yet, because I know you guys were going to ask about the numbers. But honestly, I don't really care. If you gave me that as an answer, and I would give you almost all of the credit. At most, I would take off 1 point if you gave me that as an answer. And I really try to get you to think symbolically like that, because it's a lot easier to see what's going on than if you focus on the numbers. So I could have solved it for today, and in part, I didn't want to. I wanted to give it to Amber to do it, so so you could do it. But I also wanted to show that, like, to do this problem, to do problem 1, I mean, just, again, I've been doing this for nearly 25 years, but to do problem 1, probably took me 4 minutes. And had I done it with mesh, it would have taken me at least 10, I'm sure. Right. And that's, again, I'm not suggesting that you should be that fast necessarily, but I mean, once you're familiar with these processes, this is probably half the time of what something like Nodal or mesh is. And so I'm just trying to force you to be comfortable with that a little bit. All right. All right, and I don't want to spend too much time talking about the test, but I did want to talk about it. Now, the harder one that I made the announcement during the test of saying, well, okay, you could do this one using mesh. This is a little bit of a trickier one, I think, from the perspective of somebody who's really new to this. But you know, when I say what's the short circuit caused by the 2 amp source, right? So in this particular case, I look at this guy and I say, well, I turn off the 24-volt source and the circuit simplifies into this, okay? So I can see clearly the R1 and R3 are in parallel. The part that I suspect causes people issues is this all this whole party of crap over here, right? It's complicated looking. First thing I did was I said R5 and R2 are in parallel. Why did I make the statement that R5 and R2 are in parallel? Why do I know that to be true? So why can I go from the circuit on the left to the circuit on the right? Why do I know they're in parallel?
Their nodes on each side are the same.
Their nodes on each
Okay.
side are the same, but more generally, I would say that means what?
Share the same voltage.
The same voltage. If they share the same voltage, they are in parallel. All right, that to me is the more direct way of seeing that. You're right. Their nodes are shared. That's good. But occasionally, I can have circuits that share nodes, and you know I may have something weird going on. It's a little bit less obvious. Okay. Now, what I can see from that is that parallel combination is in series with R1 and R3, right? So I simplified the circuit down to this guy, right? You guys follow this? So how I went from this one to this one?
Yeah, see.
Okay. All right, at that point, you know, basically what I say is, well, I've got a current divider to solve for this I2. And that I2 is basically the current that's going through, you know, this series combination of things here, right? So I get this guy right here. So basically what I say is to get that I2, I got a current divider. So I did current divider the way that I like to do current divider, which is I say, well, what's the voltage across this, right? You could go back to the formula if you wanted to and say I got 2 resistors in parallel. But the way I do this, I say, what's the voltage across here? Well, it's 2 amps that's splitting between these 2 resistors. So I say the voltage is 2 times that parallel resistance. And then I have to say, well, if I want to figure out this current in this branch specifically, I take that voltage and I divide by the resistance in that branch. All right. You guys, any questions about what I just said there?
So why is R5 in parallel with R2 in this case, but
Well,
not on the first case?
well, they were in the first case too, right? They were here.
I mean, exactly. Why are those?
They're parallel here, and they're parallel here,
Okay.
and they're parallel in both cases because the voltage across them is the same.
Okay.
That's the reason.
Thank you.
Yeah.
How are their voltages the same?
So if I looked at here, right, if I do a KVL around that loop, right, I would see, I don't know if I call this Vx and call this Vy. If I do a KVL around that loop, I'll see 0 equals minus Vx plus Vy, or Vx equals Vy. KVL and KCL are basically the guide path for everything we do. All of electrical engineering is guided by those 2 statements plus Ohm's law. That's all it is. The rest is just fluff. You follow that?
Yes.
All right. That's not obvious, though. I mean, I make it sound like, oh, that should be totally obvious to you. It shouldn't necessarily be. You get comfortable with that over time. All right. Anyway. All right. The rest of this, we'll post it. You guys can review it. I wanted to talk about that one. And one other thing real quick, I guess, that I wanted to talk about, which is to say, what's the equivalent resistance? I took a quick peek at some of the exams. So what's the equivalent resistance, REQ? That's the resistance that is seen looking into the terminal. So this is port A and B. So the thing to remember is people start collapsing the resistances in the wrong ways. All right, I started seeing people doing all kinds of incorrect things. When I ask for the Thevenin equivalent resistance, it's the resistance that is seen by a current entering the load terminals. That's the way I think of it. So a current that enters the load terminals is going to go through R2, and then he's going to split, right? Some of them is going to go this way, and some of them is going to go this way, and then all of it's going to come back that way. So this current and this current would be the same. This guy would be different, and this guy would be different. Don't think about current. I mean, think about current in the context of it's like water going through pipes, right? If I have a gallon of water going this way, well, I'm gonna have half a gallon and half a gallon, and it's gonna combine back to give me a gallon, right? That's the sort of think of it that way. It does help, right? So my guess from just a quick look is a lot of people probably got this wrong. I think a lot of people don't combine the resistances properly when doing Thevenin.
See, I think I actually think I got it right this part, but I don't understand why R2 and R5 are in series because
They're not.
because that says R2 plus R5.
Well, so to be clear, so it's R2 plus R5. Remember, it's that series. That's a R5 is in parallel with R4 plus R1 plus R3.
Okay.
Right. So I guess I'm skipping steps here. Basically, if you look at it, I got this guy here is R1 plus R3 plus R4, right? That is all in parallel with R5, and that's in series with R2. So one way I have to talk about this is you basically start your simplification as far away from the ports as you can. So this branch over here is as far away from the ports as I can get. So I start my simplifications there. R1, R3, make that really clear, R3 and R4 are in series. They are in parallel with R5. That combination of stuff is in series with R2. Does that make it clear, Eli?
Yeah. I actually wrote it exactly like that, but I called REQ, like I did that for the whole circuit. So the first thing I did was calculate the equivalent circuit, and I used it around, but I'm seeing how it's different when you're using superposition like this, right? This REQ is not the same as like the first case in part A. Like if you were to do the equivalent resistance in this step, would it have to be the same equivalent resistance in part A?
In part A. So I can't, in part, when you do superposition here, right? Yeah, it is. Yeah, I guess it is, right? But I mean, the question that's being asked is what's the equivalent resistance that's seen at the terminals? So it's approached the same way as doing superposition. The way that I think about, let me not think of it as a Norton, let me think of it as a Thevenin, right? Basically, there's two pieces. When I'm finding the open circuit voltage, I'm basically saying if I were to measure the voltage at A and B, what would be the impact of the sources inside this system? So what's the impact of the 24-volt source and the 2-amp source? Right, that tells me what the open circuit voltage is, right? If I put a load onto this thing, again, I think of A and B in my mind as basically the two prongs at an electrical outlet, where if I don't plug a load in and I measure the voltage, it'll be one size. And then if I plug a load in, suddenly connect a load, that voltage will drop. And that voltage drops because I'm pulling some current through it. In other words, right, if you think about it, I'm going to get this, right? So there we go. Yeah, it doesn't, Adobe is not kind to writing. If this is VOC, if I measure the voltage at these terminals, I'll see VOC. But if I then, at some time later, connect a resistor here, okay, a current's going to flow. And what's going to happen to the size of the voltage that I measure here at VAB? If I connect a resistor, what's going to happen to the size of the voltage? Is it going to stay the same, or is it going to get bigger, or is it going to get smaller?
It should get smaller because it sees resistance.
Should get smaller because if I think about VAB, VAB is always going to be VOC minus I times R Thevenin. If this is I. So basically, the way I think about it is VOC tells me the impact of all the sources that are inside that circuit. R Thevenin tells me the effect that a current at the terminals has as it flows through the resistances inside the circuit. So, you can sort of separate them that way. And this totally happens. If you look at a voltage, in your, at an electrical outlet, if you connect a load up, all of a sudden that voltage will get smaller once you start doing it, because now you're pulling current through all the resistances that are in the wall wiring. Does that make any sense whatsoever? Or am I just...
Yeah, it did. At least to me.
At least to Eli, at least to one person. All right. Now, I'm not going to go through the rest of this. That's basically all I wanted to do. But like I said, this is once I get comfortable with this would have taken me twice the amount of time to do this with mesh, right? Especially if I didn't have Matlab handy and I had to do matrix manipulation by hand, your augmented matrix or whatever, right? That would have taken me some time. And personally, I would be less comfortable with that for sure. Okay. And then, like I said, I'm not going to go through the rest of this. I'll post these up here. You guys can take a look at the specifics of how I approached it. Okay. All right. Any questions about that? Okay. All right. I want to talk about one other thing here real quick. I made an announcement this morning about specifically about homework 2 problem 1. All right. And it's going to be slow to load up. So let me go ahead and all right, I modified the, oops, this is the wrong homework. Here we go. I modified the PDF as well. So let's look at the PDF here real quick. So there's a little bit of a problem I think some of you guys may have experienced with this, which is basically in these equations here, A1, A2, and A3. If I look at this equation here, the top one, and this equation here, the bottom one, problem you have is there's potentially infinitely many values you could put in for A1, A2, and A3. Because, I just, for sake of argument, let's say the first equation was V1 plus V2 plus V3 equals 0. Technically, you could multiply both sides of that equation by 2, and effectively you have the same equation, right?
Yeah.
In other words, there's a question of, in linear algebra, what you call linear independence of the equations, right? So that was a mistake on my part. So what I did here is I need to give you in each of these equations at least one constraint. And so what I did was I told you what the value of A1 and A7 are. All right. So once you know those values, and this guy is the number 2. Once you know those values, you are then pinned on what everything else needs to be. All right. So going forward, I'll make sure that that's taken care of. But That's just an essential element for those things. All right, so my apologies that I did not constrain that, but if you had an issue with that before, it should be fine now. All right. Any questions about that?
Nope.
All right, let's get to it then. All right, so where is my examples? Okay, so today we are going to do 2 examples, and these are all developed in Matlab. Last time I showed you guys my Matlab code. I'm going to post the Matlab code that I use here so you guys can see it as we go through it. All right, so here is the process. All right, I'm always going to use this process. Steps 1 through step 6. Now this was in the slides that I posted on Monday, but I'm going to post another set of slides, which is just simply a summary of each of these steps. All right, I'll post those later today, but I'm going to do 2 examples here. And I may possibly go past 3:45 to finish the second example. And if you have to go, that's fine. I'll end up posting the video that has the complete example. Okay. All right, so we're going to go through those steps. And let's start with this guy. All right. So the 2 examples here today, some of you guys are going to say, well, step 1 is always to get the equation, and the equations are always the same. Well, they're not always the same, right? Because I might give us something just to look ahead. This is one of the ones we're going to do. If you look at this guy here, this is not the same as the ones that you've seen so far. All right. So you'll see why getting the differential equation is important. Okay. All right. So let's plow forward with this guy. All right. So we want to find IL of t. All right. So our step 1, find the differential equation for t greater than 0. It needs to have the form that I've given it there. Okay. So I got to get those coefficients A, B, and C. So how do I do that here? How do I get a differential equation for I sub L? What's the circuit approach?
We start with KCL.
Nodal. Yeah, KCL and nodal, basically 2 ways of saying the same thing, right? So if you look at this, it says at t equal to 0, that switch is going to open up, all right? And again, for somehow, some way, we don't know how this happened, but somehow 10 volts got itself onto that capacitor, all right? So that's important to know. All right, and somehow IL is also 0. Again, that probably would have been hard to happen, but you've been told that's the case. All right, if you've been told that's the case, great. Okay. All right, we have to do nodal analysis here to get this. So we got to do a KCL. So I'm going to say for me, it's at that top node. I'm going to say I is the current going in, and I has to be equal to IC plus IL plus IR. Right? I start at a pretty high level. Okay. Now, how do I go from there?
Represent them in terms of volts.
Represent them in terms of volts. Well, remember, I want to get a differential equation here in terms of I sub L. So how could I do that?
You could plug in the relationships that we know of the passive components, like
Okay.
VL equals LDI dt. You could derive expressions using those.
Yep, VL equals LDI dt. Okay, great. What's the other one? Is it Musa?
Yeah, IC equals C dV dt.
Yeah, IC equals C dV dt. And the thing I can see about this, the capacitor voltage and the inductor voltage are what in this case?
They're the same since everything's in parallel.
All right, so that's all the same. All right, so that says that for the capacitor current, right, I have that in terms of the inductor voltage right off the bat, don't I? So that's helpful already. Okay, so if I try to do this. So the capacitor current is C dV dt. Inductor current here. All right. What should I do to start trying to build this guy up?
dt.
Shouldn't we multiply also everything by ddt, or does that go a little bit later? Because I was reviewing the notes like earlier, and there's a point where in order to, I think, get it to a second order differential equation, we multiply everything by ddt.
I think that depends on if there's integrals after we plug everything in, and we haven't plugged anything in yet. So we could probably plug in C dV dt for IC, and then you could plug in VC over R for IR.
I thought we wanted it in terms of IL. We couldn't plug in
do.
CD.
Yep, we do want it in terms of IL. That's right. So where does that lead me to? Probably starting with.
You could divide the C over and then multiply over dt, and then do the integral, and then you have a representation of VC in terms of IC.
Okay. Let me give you a hint. Let's use this guy. So let's think about how we could use that I sub R right there. I sub R is what? Help me with Ohm's law on that guy.
E of L over R.
V over R, right? We've labeled this guy as V. So that's now. How can I get that in terms of inductor current?
LR di dt.
Well, L over R.
Yeah, L over R. No, yeah. L over R. Yeah.
DIL by dt. Okay. And with the capacitor current, how can I get that? Right.
1 over C integral of IC.
No.
It's just going to be the derivative of VL.
Yep, the derivative of VL. So that means it becomes the second order term, LC DIL by dt.
D squared I.
Yes, D squared IL by dt squared.
So what did we do there? We multiplied ddt.
We didn't multiply, right? What we did was we said, okay, IR is V over R. First of all, that makes sense, right? Just to
Yeah.
Okay.
Mm-hmm.
So what I did was I said V is substituted in here. V is L di dt.
Okay, I see that.
And then similarly down here, I said I equals C dV dt. So that's substituted in.
Because C dV dt means C times the derivative of voltage, and we know what the voltage is, so we just took the derivative of that expression.
That's right. So yeah, if you look at C, if you think about it this way, it's C times d by dt of the voltage. You plug in there L DIL by dt. When you take the derivative of that, it is this, like that. It's the second derivative, right? All right. So now all I got to do is I got to plug in for IC and IR here. So I'm going to plug it. If I plug in for IC, I get LC d squared IL by dt squared plus IL. That's just IL. And IR is L over R times DIL by dt. Okay. Now, how do I get that in my standard form?
Divide by LC.
Divide by LC. Divide both sides by LC. So basically I'm going to say I got I over LC equals D squared IL by dt squared plus, what was that guy? Plus 1 over RC DIL by dt plus 1 over LC times IL of t. Okay. And that looks too big. Okay. All right. What do I need to do next? I've got my differential equation, right? That's in the right form. So what do I do at this point?
Professor, I have a question.
Yeah.
Do you ignore the switch when you're doing the first step?
Yeah, so specifically, right, we do it for t greater than or equal to 0, right? So for t greater than or equal to 0, we say, well, what's going to happen after t greater than or equal to 0? Well, the switch is opening at t equal to 0, so the switch doesn't matter, right?
Okay,
If
thank
the
you.
switch is open, it's an open circuit. So that's important, right? I mean, it's a good question, right? Is to say that for t greater than or equal to 0, the switch is open. So make sure that you look at the switch in the appropriate location for t greater than or equal to 0.
I'm still kind of stuck on the sub you do on IC. I know IC is C dVdt. I'm just not seeing where the L DIL squared dt is coming from.
Well, because, so we could pull this offline if we have to, but V equals L di dt, right? The voltage on the capacitor and the voltage on the inductor are the same. So I can basically substitute in L di by dt.
Oh, I see
The
where
voltage, right?
the voltage C dVdt is actually the voltage of the capacitor. I see that. Okay.
Yeah, right. That's the key. Yeah, this guy up here is really key to being able to make that happen. Okay. All right. So this guy's in my standard form, right? My standard form, we said, was I have some constant. So this C thing is problematic. This is little c equals d squared x by dt squared plus a dx by dt plus b times x. So I can see right now what a and b are, okay? And I can see what c is as well. So what's step 2, right? Well, step 2 is solve the differential equation and find the general form of the solution. Now you may have ways that you want to do that. I have ways that I like to do it, which are not necessarily the same as iBooks, but I'm trying to be consistent with that. So what did I say we wanted to do to figure out that form of the solution? What's our key step there to figure out that form of the solution?
You gotta find alpha and omega.
Find alpha and omega, right? And to do that, we basically, need to remember that this guy is, really d squared x by dt squared plus 2 alpha dx by dt plus omega naught squared times x, meaning, and this is in my summary notes, and it was there last time too. Alpha is a over 2, and omega naught is the square root of b. Okay, at that point I got everything I need. Okay, now keep that, and I'm going to go over here to the Matlab code that I wrote. All right, so here's what I do when I'm approaching a problem like this. Okay, so just to be clear, here's the circuit. So it's got 25 nanofarads, 25 millihenries, and the R value, I didn't write the R value down, but the R value is 400 ohms. For whatever reason, the textbook I took this from did not have that. So let me put that in. R is 400 ohms. Okay. All right, so if you look at my MATLAB here, all right, I put in those values. And I put in the I value as 24 milliamps, and I also put in here the initial conditions I was given. And then I calculated A and B, and then I calculated my alpha and omega. Okay, so I'm going to take that. Now, again, I'm working in MATLAB and not in the Canvas editor, so I'm just going to take that guy. And if you do that, I can right click on this, and then I do evaluate selection. And I'm going to look in the command window, and it's going to tell me the values I've got. So there's my alpha value, and there's my omega naught value. All right, so 5 times 10 to the 4th is 50,000. and omega 0 is 40,000. So somebody who knows this, so omega 0 is 40,000, alpha is 50,000. What am I looking at? What kind of dampedness am I looking at here?
But overdamped?
I'm looking at overdamped, right? And if you don't remember that, I can go to my summary slides here, and there they are, right? If alpha is less than omega naught, underdamped. In this case, I got alpha greater than omega naught, right? So he's overdamped, right? So that means my roots look like this guy, right? Minus alpha plus or minus square root of alpha squared minus omega naught. Now, you can do that different ways, right? You could look at what we call the characteristic equation, and you could just do the roots from the quadratic formula, right? There's some other ways that are even easier to do that in Matlab. But what I did in this particular case is I said, all right, it's overdamped. I know alpha, I know omega. So I know that this here is the form of my solution. This x of t equals a1 e to the s1t plus a2 e to the s2t plus the steady state. I know that's the form of the solution at this point. And I know these are the roots. So if you look at what I did in my code, right? I defined S1 and I defined S2, okay? And I just plugged straight in to what those formulas were. And then I've got my two coefficients, or not my two coefficients, my two exponents, okay? Questions about that?
Oh yeah, what do the roots do right here? Like what does it represent?
Well, this is second order differential equations, right? So what we're saying is I have, when I solve the differential equation, right? I'm basically, I'm given a differential equation that has the form that's shown right here. And let me go full screen on this guy, right? So I have this differential equation, okay? And in differential equations, what you learned, right, is I get a transient, or what they called homogeneous, and a steady state, or what they called particular, right?
Mm-hmm.
What you do is you say, and I talked about this on the very first day, is to figure out the transient solution, you look at what we call the homogeneous equation, right? And you look at this guy and you say, well, d squared x by dt squared plus a dx by dt plus b x of t equals 0. The solution to that is the homogeneous solution, or the transient solution. And you guess that the answer to that is basically, some a e to the st. You plug that in and you get this thing called the characteristic equation. And the roots of that equation, which I get from here, right? The roots of that equation are the exponents in those exponentials.
Gotcha.
Okay. So yeah, that's part of the reason what I don't like about this is we're turning this into a process that lives on its own and exploits the results of differential equations, when in fact the results of what you learned in differential equations are really pretty easy to just apply straight away. So you could do it other ways. Like this particular step, if you're comfortable, just doing this from differential equations, I would accept that way as well, to get the form of this thing. All right. Does that answer your question?
Yes, a lot clearer now. Thank you.
Okay. Yeah, and we talked about that on the first day, but we're kind of drifting away from that time-wise, right? But if you go back to the first lecture and you watch that video, you'll see that there too. Okay. All right. So at this point, what I know is I've gone through, I've figured out those values. What I've determined now at this point is that my IL of t has the form, and again, if I want to see that, I can go back to the summary slide here. Go back to the summary slide, and it's written here. It's overdamped, so this guy is my form of the solution. Okay. So I say IL of infinity plus A1 e to the S1t plus A2 e to the S2t. And again, you can see how I do that in my Matlab code. I don't put numbers in there. I just leave them as variables. That way I can see everything, and it's a lot easier for me to keep track of what's going on. Okay. All right, so I finished step 2. So now I got to go to step 3, which is to get the steady state values, IL infinity, VC infinity. So in this case, I don't need VC of infinity, but I'm gonna try to see if we can figure it out anyway. All right, so let's then say, here's our circuit. Let's drop it here, okay? So what do I do in this step? How do I figure out IL of infinity and V of infinity? What's the approach?
Open the capacitor and short the inductor.
You got it. Yeah. So I say I still got my current source. My capacitor becomes an open, and my inductor becomes a short, and the resistor is still there. Resistor never does anything interesting. All right, V. All right, that's V of infinity, and this is IL of infinity. Okay. All right, V of infinity. Let's start with that first. What does that equal to?
It'd be 0 because of the short, right?
0 because of the short. That's right. 0 because of the short. If I do a KVL around a loop that includes the short circuit and this V infinity, it would be 0. Okay. So what about IL of infinity? What would that be?
I think, what was it? Whatever the current source is.
Yeah, whatever the current source is. I'm calling I because that's what this guy was called here, which is 24 milliamps. Right. So if I look at my Matlab code that I wrote, right, I defined that I was 24 milliamps, and I just say at this stage, I inf is I, right? Again, allows me to kind of track stuff easily if I can just look at the equations in here, okay? All right, so step 3 is done, all right? Now on to step 4, all right? Analyze the circuit at t equals 0 minus to find either VC 0 minus or IL 0 minus. Now, I say analyze the circuit at t equals 0 minus. In this case, I've just given you what you need, all right? I've given you the initial conditions here, right? I gave you IL of 0 minus, and I gave you a V 0 minus. So I don't need to do any analysis. This step is easy. Now, my next example, that's not going to be the case, all right? But in this case, it's an easy one, right? So looking at this, step 4, right? Step 4 says figure out the values at 0 minus. And then what do we know about capacitor voltage and inductor current? They have to be continuous, right? So if I have 0 minus, I also have 0 plus. Okay. All right. So my step 4 here, so now I'm step 4. All right. Step 4, I have IL 0 minus. We were told was 0 amps. V of 0 plus, the capacitor voltage, we were told was 10 volts. So that tells me what IL of 0 plus is, and that tells me what V of 0 plus is. Okay? Questions about that? That's pretty straightforward. Okay, now I got on to step 5. All right, step 5 is to get my other initial condition, right? Analyze the circuit at t equal to 0 plus, specifically at t equal to 0 plus, and find these values here. Right.
Wait, quick question.
Yeah.
So VC 0 minus and VC 0 plus, are they always equal or just
always equal? VC 0 minus, VC 0 minus and VC 0 plus always equal. IL 0 minus and IL 0 plus always equal.
Okay, thank you.
That's the key thing, because we talked about it. We gave a physical reason for that, which is to say energy has to always be continuous. So if that has to be continuous, then the energy storage variables have to be continuous. That's in words what this means is that voltage is always continuous. It can't have a jump. I can't go suddenly from 4 volts to 5 volts on a capacitor. That can't happen suddenly.
Would that be the same thing for VOC and V infinity as well, right? I know that may be like unrelated, but
no, that's a completely separate thing, right?
Oh.
Capacitor voltage and inductor current, but all this says is those things are always continuous. In other words, they can't. So it has to be a smooth. If I looked at voltage as a function of time, right? So If you go back to the first lecture on this, I did sort of an example where I looked at a simulation on this, but the capacitor voltage has to be smooth and continuous. It could never just suddenly go like this. I couldn't have a discontinuity is what you would call that in math. And I can't have a discontinuity because the physics just say it's not possible to do it.
Okay.
In other words, if you think about it, if I had a capacitor that was charged and I suddenly, all of a sudden put a short circuit across there, I had energy stored in that guy. What's going to happen to the energy stored in that? So if I took a capacitor and let's say I put a screwdriver across the terminals. Anybody know what's going to happen if I do that? That's a short circuit.
Discharge. Yeah.
It'll discharge, but yeah, it'll discharge with a bang, right? I mean, if you did
Yeah.
that, you would boom. I mean, you would see a giant flash.
Instantly discharge or something?
What's that?
I say stop quickly.
It would if I did that, it would discharge, but it would discharge into a giant flash of light, right? You would just see this giant. In fact, I'd be happy to do that at some point. Charge up a capacitor, drop a screwdriver across it, and you'll see it. It's just a giant flash. Essentially, because what you're saying is I had energy stored in a capacitor, and the basic truths of nature are that energy is always conserved. So if I had energy in the capacitor, it's got to go somewhere. It's got to go somewhere fast. So it's going to become light in that case. All right. So that's a good physical thing to understand. But, in terms of you trying to figure out the answer to the steps in the process, V0 minus and V0 plus are the same. IL0 minus, IL0 plus are the same. Okay. Those statements are not true about any other variables. They're only true about the capacitor voltage and inductor current. Okay.
Got you.
All right. So, step 5, analyze the circuit at t equals 0 plus, specifically 0 plus. So if I say 0 plus, what do I mean when I say 0 plus? What's implied by that?
Like the switch is open.
Switch on.
The switch is moved, and it's the instant, it's the nanosecond or the picosecond or the femtosecond or whatever after the switch has moved. So in this case, the switch has moved from a closed position to an open position. Okay, but it's the instant right after that switch is moved, and not all the time after that switch is moved. It's the instant right after it. Okay. So that what that says is what did we say because of the constraint from step 4? What did we say is true about the capacitor and the inductor for that really short period of time, right as the switch is moving?
They're gonna act like an open circuit and a short circuit?
Not quite.
They're gonna act like sources.
They're gonna act like sources, right? What's the capacitor acting like?
The voltage source.
Yep. And what's the inductor acting like?
Current source.
Current source, right? That's the key thing. So then what I want to do is I want to look at that circuit again here in step 5. So let's go to step 5. And let's paste in here this character. All right. So right after that switch opens up, I got current source, I, and I said the capacitor becomes a voltage source that's got VC of 0, which is effectively a 10-volt value. All right, and then the inductor is a current source with 0 amps, which is, kind of a funny thing, but it's a current source with 0 amps. And the resistor is just a resistor. Right,
Why doesn't a current with 0 amps act like a short circuit?
Current with 0 amps could never, ever be a short circuit. A current source with 0 amps means how much current's flowing through that branch.
Okay.
0.
0, right? So that's a what kind of circuit? Not a short, but a what?
Open.
Open.
And Dr. Cox, is there a reason why the polarity for IC is positive minus versus negative minus?
Current flows in the positive direction.
Got it.
Hang on. I'm not quite sure what you're asking. So you talk about this IC?
Yes, because the IL is flowing, well, you're 0 amps essentially, but you're going in the direction of IL. And then for,
No, well, I mean, so IC, IL, and IR were just all defined that way. All right.
okay.
So, but the thing to remember about this is if I had a capacitor like this, and I said, here's V, and here's I, right? That says I equals C dV dt. Okay. You're asking a good question, Anthony, right? So if I had this, now what happens if the current was going this way?
It would be backwards. It would be minus plus.
There'd be a minus sign, right?
Minus. Okay.
Yeah. All right. So I got to be careful about that kind of thing. Passive sign convention still applies for all. Passive sign convention applies no matter what. All right. Always applies. Okay. So at this point here, right? So that's what, so the 0 amp source is basically there's no current flowing through there. So the thing that, what I ask for, is I am doing this step because ultimately at the end of the day, if I'm solving for the inductor current, I need to know what DIL by dt is equal to, right? I need to know what that value is, okay? So that tells me I need to know VL of 0 plus divided by L. First of all, that statement right there that I just wrote, that should make sense, right? Any questions about that? Okay. All right, so what is VL of 0 plus?
I want to say, wouldn't it be VC over R? But
Well, you're close. I'm looking for the voltage across the inductor. What's the voltage going to be? Just VC of 0 plus.
yes.
Right? Right. The voltage across the inductor is the same as the voltage across the capacitor. So I have everything I need right now to get the initial condition on that inductor current derivative, right? That's what we're doing. We're trying to get the initial current for that inductor current derivative. So in my code here, move this guy over to the side. All right, let's look at how I did that. So what I did was I defined this variable here, VL at 0 plus is the same as my initial voltage, okay? And I said my initial voltage was 10 volts, okay? And then what I did was I said DIL, that was the variable name I gave for the derivative here, is I said DIL is VL 0 plus divided by L. Okay.
Can you explain how you got that top equation again?
Which top equation? This one?
Yeah.
I just took VL equals L di dt, right? And I'm explicitly evaluating at 0 plus. But if you look at that, well, that says that just doing your algebra, right? Di by dt is V over L.
Okay, I see it. Thank you.
Yeah. Okay. All right. Questions? More questions? All right.
So is the ILDT 0 plus different from the ILDT at any other point?
Yes. Yeah. Remember, DIL by dt. It's a continuous function. So IL is always changing. Its derivative is always changing. I'm explicitly looking for what is that derivative right after the switch moves, because I need that for my initial condition.
Okay.
Make sense?
Yeah, it makes sense. I just assumed since DIL over DT, since like we're building a whole equation with respect to time, that it would like fit that accordingly. I don't know how to explain. I just assumed that like DIL DT would be the same throughout the whole period in time throughout the circuit, because that's for the equation we're building.
DIL by dt is a function, right? I mean, it also changes as a function of time.
Okay.
Right? I mean, think about it. What's going to happen once I get to steady state? Once I get to steady state, an inductor becomes a short. So I know at that point in time that the inductor current stops changing. I know that its derivative is eventually going to go to 0. It sure as heck isn't going to be 0 initially.
So we're just finding the initial start of where it is.
And I need that because remember what I have is the solution to a differential equation, and differential equations always require two initial conditions, one for IL and one for its derivative.
Okay.
Right? So it's bad to think of this process as different than anything you learned in 2254 or in 21 or whatever the differential equations 3432 or whatever, right? The process that we're doing here, we're using the physics to figure out what our initial conditions would be. Whereas if you were in differential equations, they would have told you IL of 0 is whatever number and DIL by dt of 0 is whatever number. Okay.
Yeah.
All right.
I can also see how, yeah, like that explanation, how it would be different, like the derivative throughout time makes sense because it makes sense to account like all the points in time to model it properly.
Right. Right. Okay. All right.
If you were to analyze like t equals 0 plus, but instead of a current source, you had a voltage source, how would like the inductor voltage at 0 plus and the current or the capacitor voltage?
It all depends on the circuit, right? So let's look at that. The next circuit I've got has a voltage source, so we'll look at that there, right? If I was a voltage source instead of a current source, this problem wouldn't really work, right? But the next one we'll do that.
All right.
Question I want to figure out here is also, I mean, even though I don't need it, just because it's good practice, I want to figure out the current in the inductor, right? So that's, or sorry, the current in the capacitor, which is IC0 plus. All right, IC0 plus. So what is IC0 plus? How would I figure that guy out? How would I figure out IC0 plus?
Minus IR.
Do what?
The I naught check by IR.
Well, you're right, but so you got that doing what? KCL, right?
Yeah, KCL.
Yeah, so KCL, right? So if I do KCL at the top, right, what I see is I have a current I going in, right? That the I goes in, and I have IR coming out, and I have IC0 plus coming out. And IR in this case is VC of 0 divided by R plus IC0 plus. Okay, so that tells me that IC0 plus is whatever that current source is minus VC0 plus divided by that resistor. Right? Questions about that? And I'm saying 0 plus, 0 minus. I mean, they're all VC0, VC0 minus, VC0 plus are all the same. All right, go away. All right, questions about that? All right, so in my Matlab code, all right, I put in, so there's that expression, IC0 plus is I minus the initial voltage divided by R, and then I get my derivatives, okay? Now I'm on to step 6. Step 6 is, okay, well, we had this guy. All right, so let's drop this over here. All right. So we had this. Step 6 is basically, all right, I have now a number. I have IL of 0 is equal to 0 amps. I have DIL by dt right after I move the switch is some number. Again, I can go into Matlab and get that number, but I got it now, right? So what I can do is I can say, well, let's get IL of 0 and let's get DIL by dt of 0. All right, and let's plug those numbers in, right? So if I go into the top one, I get it's IL of infinity plus, what happens to those exponentials when I plug in t equals 0?
Become 1.
Become 1, right? So this guy becomes A1 plus A2. And then I got to take the derivative of that whole thing. I don't want to do that because, I basically am giving you, because it is inconvenient to have to do it every time. right? What I gave you was, if I'm looking at the overdamped case, that's what I've got here. You take the derivative, I get this expression right here, okay? I get these values, all right? So the equations in that case, all right, equations in that case are IL of 0 equals IL of infinity plus A1 plus A2, and IL of, or DIL by dt, sorry, of 0 plus is equal to A1 S1 plus A2 S2, right? I just looked those up. I've got numbers for S1 and S2. What I don't have is A1 and A2. I don't have those unknowns. Everything else, so this IL of 0 is a number, IL of infinity is a number, S1 is a number, S2 is a number, and this guy is a number. Those are all numbers I've got. And so what I do is I say, all right, I'm going to turn that into IL of 0 minus IL of infinity DIL by dt 0 plus is equal to 1, 1, S1, S2, A1, A2, like that. Okay? If you multiplied out those matrices, right? If you multiplied out 1 times A1 plus 1 times A2, that would give me this first equation. If I multiplied out S1 times A1 plus S2 times A2, I'd get this equation. Okay? What I do, I jump over into Matlab, all right? And I defined those. So let's compare them here. Here's Y. All right, what I did was I took so IL0 minus I infinity. So IL0 minus I infinity, that's the top line. I put a semicolon in there to then enter the second line. And then I called this matrix here C. So I did 1, 1, semicolon, S1, S2. The semicolon jumps to the next row, right? And then I did A equals the inverse of C. That's this guy. So I looked at it as, when you look at this later, Y equals C times A. And I said that A equals C inverse times Y, right? That was my way of entering this into MATLAB. And I'll give you guys the MATLAB code as well. All right. And then this expression here, I also in my summary slides have this. Okay. So basically, these are the three forms of what that equation would look like, right? So since I'm looking at overdamped, I look at this character, right? It would be I in this case instead of V, right? No big deal. Otherwise, it's the same. All right. And we've got this right here. Okay. I plug that in. Right? And notice what I did here. A of 1 means it's the top value here. A of 2 means it's the bottom value. And then I make a plot. Okay. So let's do this. So what I do is I highlight all of that. I right click, evaluate selection, and there he is. Okay. So let's take a look at this picture. So what I just plotted was the current there. Move this. All right. Let's see if it makes sense, right? So where's this guy starting at 0? Why does that make sense? Why does it make sense this guy starts at 0?
And initially it was at 0.
Yeah, if I looked at my initial condition, right? My initial condition that I was given was that, right, was that he started at 0. And then he ends, if I look at where he ends, right? He ends up here at, looks like, if I hover over that, I can even see it. Looks like he ends at about 24 milliamps, right? So looking at the y-axis here, it looks like this guy's ending up at about 0.024, right? Which is what we said it would be, because eventually all of this current flows in the inductor, and that's 24 milliamps. Okay. All right. Questions about that? Probably lots of them. All right, you guys are at the end of your attention span. So I'm gonna go a little bit longer, and I'll work my second example as a separate video that I'll post later, but I want to go a little bit longer and at least start step one for this guy. Okay. So let me look at this. So step one is what? What do I want to, what is my step one? Anybody even remember that?
Write the differential equation.
Yeah, write the differential equation. So I'm going to call this character up here, this 4 ohms. I'm going to call him R1. I'm going to call that character R2. Okay. All right, and I'm gonna try to follow it that way, and I'm gonna try to follow my signs. Now this one is not just a straight up parallel circuit. Now, I'm gonna do this again, but I just want to get through writing the differential equation here. Okay, so let's jump down to where that is. Okay, how do I start? So after t equal to 0, the switch is gonna close, right? So at that point in time, this guy's gonna be a short like that. Right? So where do I start? My goal is to get the capacitor voltage.
So if they're looking for voltage, I normally do KVLs, right? Where you go in the loops.
Well, maybe. I
No.
do need to do a KVL here for sure.
If you find the voltage across R2, isn't that the same voltage across the capacitor?
It is. Yep.
So do a KVL of the left side of the circuit and
Okay, do a KVL on the left mesh there. So let's say 0 equals, I'm going to go this way around like that. So 0 equals -12 plus, now I go through the 4 ohm resistor, which I called R1, then I go through the inductor. So I'm going to say I go through R1 times I, because we've called that current I. What do I do for the inductor? What's the voltage across the inductor?
V of L.
V sub L, yeah, I'm gonna write in there. So what do we know? We know that V sub L is L DIL by dt. Okay. And what do we know about the capacitor current? IC equals what?
CdVdt.
CdVdt. All right. In this case, just to be super clear, I guess I called it VL, but it's been called I in this particular picture. I'm just going to write in L di by dt. And again, it's positive because I have a current flowing into the plus terminal. All right, now I got this parallel combination of the resistor and the capacitor. So in my KVL, what should I write for that?
Could you repeat that prompt one more time, Dr. Cox?
Okay, so as I'm going around, I'm going around this outer mesh here, or this mesh here. So I go minus to plus on the 12-volt source, then I go plus to minus on this 4 ohm resistor, then I go plus to minus on the inductor, and then I'm going to go plus to minus across the parallel combination of the resistor and the capacitor.
Mm-hmm.
So what's the voltage across the parallel combination of the resistor and the capacitor?
VC.
Yep. I'm just going to write plus the capacitor voltage. Now that's good for me for now, right? I'm happy with that because, as I look at that, I want to get to the capacitor voltage. All right, so that's good for me. What else do I need to do? I need to get rid of, I want a differential equation for the capacitor voltage. I want to get rid of the current. Right? I don't want the current to be here. So what could possibly help me to get the current out of that picture? We basically did an equivalent of mesh analysis by writing a KVL. What's the other trick we got up our sleeves?
Relating to mesh?
Well, we have two. So fundamentally, at the end of the day, there's only two things we know, three things we know. We know Ohm's law and I guess Ohm's law is buddies, right? Which are these
V
two.
equals IR. Just use Ohm's law for I.
All right, so I got three tricks. I got my Ohm's law stuff. So basically V equals IR and those things. We did KVL. What's our other trick?
KCL.
KCL. All right. We only got one node to work with here, right? So which node is that?
The one in with the middle branch.
This guy right here, right? So why don't we say this? I can say I, which flows into that node, is equal to the current that flows through R2, right? So what I labeled as I2
Plus IC.
IC. Okay. So help me out. How can I fill in something for I2 and for IC?
Well, I2 is just V2 over R2.
Yep, and since the voltage on that 2 ohm resistor is the same as the capacitor, it's the capacitor voltage divided by R2. And IC is C dV dt. Now looking at that, I got two equations and two things I don't know. I and V, I can combine those and I've got one differential equation. Okay? That means what? That means that this guy, equation 1 here, needs to go into this guy that I'm going to call equation 2. All right, so let's take equation 2 and rewrite that as 12 equals R times I plus L di by dt plus V. And then what I'm going to do is I'm going to substitute I into that equation. So R times I, that means plug in this whole thing. R times, I should be careful, this guy was R1, right? So I'm going to plug in that whole thing. So V over R2 plus C dV dt. That's the first term. Okay.
Do we need to take the derivative of I now?
No, I just plugged. So this is I right here, right? I plugged I in right there.
Yeah, but for di dt, don't
Well, now I got the next term. So this was the first term, right? Now I have L times d by dt of I. So I plug in V over R2 plus C times dV dt. Like that. Plus V. Now, without me simplifying that, which I can, right, and I will, but without me simplifying that, what do I see? Well, now I got a second order differential equation. Where's the second order-ness coming from?
That second term.
Yeah, this middle term here, right? So I've got a derivative d by dt. So I take the derivative of v and I take the derivative of dv by dt. The derivative of dv by dt is the second derivative, right? So this guy is going to become d squared v by dt squared plus a dv dt plus b v equals some
v
constant. Okay. Now again, I'm not going to do that simplification right now. I think I've worn you guys down for enough for now, but I will post that the remainder.
R goes to 0, right? Because everything